In this video, I will be explaining question number 1 of homework 10. So, for part A, we have to define what is the Poisson process. So, we know that a stochastic process xt is called Poisson process if the number of points n in the interval t1 comma t2 with the parameter lambda t where t equals to mod of t1 minus t2 follows the probability distribution that probability of n equals to k is equals to e to the power minus lambda t into lambda t raised to the k by k factorial. So this is the Poisson distribution, and this is from where the name comes from. So now let's look at the next property. The next property says that if the intervals t1 comma t2 and t3 comma t4 are non-overlapping, then the probability of the points, that is, or the random variables between the points n of t1 comma t2 and n of t3 comma t4 should be independent of each other. And the third point says that at a time moment t there is not more than one Poisson point. So if we collect the properties of the Poisson process, we will get that the mean of the Poisson process is lambda t. The autocorrelation r t1 comma t2 is equals to lambda squared t1 into t2 plus lambda into minimum of t1 comma t2. So now see how this can be interpreted. So we see the mean is actually lambda t. So that means with the longer intervals, the probability of success actually increases. So that is actually understandable in real world, because as the interval increases, the probability of occurrence of event also increases. So that is defined in the mean. So now let's look at the process which is called Poisson increments. So we say that Poisson process xt, suppose we have a Poisson process xt and we have a constant lambda that is greater than 0, then we define a new process yt which is equals to x of t plus epsilon minus x of t upon epsilon. So we see that the probability of yt equals to n over epsilon can be defined as equals to e raised to the minus lambda into epsilon whole multiplied by lambda into epsilon raised to the n by n factorial. So this is very simple, comes from the Poisson distribution. Again, we see that the mean of these Poisson increments is lambda. Note that this mean is not dependent on the time t, and autocorrelation rt1 comma t2 is equals to lambda square if mod of t1 minus t2 is greater equals to epsilon, and it is lambda square plus lambda upon epsilon minus lambda into mod of t1 minus t2 upon epsilon square if mod of t1 minus t2 is less than epsilon. So this is understandable. Why? First of all, we see that for a Poisson increments, the mean is constant, the expectation is constant as that is expected, because it really depends on epsilon, which is a constant. And also the autocorrelation, if the difference between t1 comma t2 is greater than epsilon, that means they are non-overlapping, so it comes to be lambda squared and constant. But if it's within the difference, but if the difference is not greater than lambda, so we can assume that they have a conflict like this, it lies in this region. So it really depends on lambda and epsilon both. So that is seen here. Next, we define what is Poisson impulses. So Poisson impulses is nothing but the limiting case of Poisson increments, where zt is defined as differentiation of xt, which is limit of yt where epsilon tends to 0. So now z of t can be defined as this, that is, it has values 1 at certain moments. So as we see, as is the case of uh, Poisson increments, the mean was constant lambda. So is this the case with Poisson impulses? The mean is constant lambda because all the points have the same value, and also the autocorrelation is lambda square plus lambda into delta of t1 minus t2, where delta is the impulse function. This is really understandable because we see, other than the, as in the Poisson increments, we see if t1 minus t2 is greater or equals to epsilon, it was constant lambda square. So that happens that if t1 minus t2 has value other than the points t1 minus t2 or this moment, the this becomes 0 and the autocorrelation again becomes lambda square, or otherwise at the moment at the points of t1 minus t2, that the impulse points, it has other value, just as in the case of Poisson increments with the limit epsilon tends to 0. So now comes the definition of semi-random telegraph process. Again, we consider the random selection of points with density which follows Poisson distribution. That is, probability of k equals to e to the power minus lambda t into lambda t raised to the k by k factorial. So this is a graph of a semi-random process which can take only two values, 1 and minus 1. So we define a semi-random stochastic process if x of 0 is always fixed at 1. So x of t is equals to 1 if k is even in 0 to t, and is minus 1 if k is 1 in odd, k is odd in 0 to t. So we see that the mean can be defined as, or if we calculate, so we get the mean as mean of a random process would be e raised to the power minus 2 lambda t, and its autocorrelation is equals to e raised to the power minus 2 lambda into mod of t1 minus t2. So this is understandable because we see the mean is e raised to the power minus 2 power of lambda t. That is, as we see a semi-random Poisson process can take only two values, 1 and minus 1, and as t tends to infinity, we can safely assume that the number of occurrences of odd and even would be same, and so as t goes to infinity, the average would be 0 because it can take only two values, 1 and minus 1. So that's pretty simple. And also it satisfies the property x of 0 is, if we put t equals to 0, we will get 1, that is at point 0 at time 0 the expectation is always 1. Now we see what is random telegraph signal. Suppose we have another random variable theta independent of x of t with theta of probability of theta equals to 1 equals to probability of theta equals to minus 1 equals to half. So then we can define a new random variable yt, which is called also the random telegraph signal, where y of t equals to theta of x of t. So we see that if it's random, then it can take only two values, 1 and minus 1, and so its expectation should always be 0. As that is the case, expectation is 0, and autocorrelation r of t1 comma t2 is equals to e to the power minus 2 lambda into mod of t1 minus t2. That is, autocorrelation only depends on the interval t1 and t2. So now we define what is a random walk. A random walk, suppose we have a random variable x n into t equals to k of a ks minus n minus k into s. So now we define x of t as a random walk, that is x of t equals to x of n into t, where t lies between nt and n plus 1 into t. So now probability of k equals to n choose k into p raised to the k into q raised to the n minus k, where p could be, where it has two outcomes, success and failure. Suppose the probability of success is p and the probability of failure is q. So we will see that that the mean of this we will see that the mean of this random walk would be 0. Suppose if we consider a random coin tossing in event for this random walk, then we see that p would be half, q would be half, and suppose there are two outcomes only, plus 1 and minus 1. So in that case, we will get the mean as equals to 0, and the autocorrelation would be minimum of m or n multiplied by s square. Now we define what is a Wiener process. So a Wiener process is a limiting case of random walk, that is w of t equals to limit of xt, where s tends to 0, t tends to 0, and n tends to infinity. So let us go to the random walk again. So this is the definition for random walk. So this s tends to 0, this capital T tends to 0, and this n tends to infinity. So if we take the probability density function from this, we will get the probability density function is 1 upon root over of 2 pi alpha into t into e raised to the power minus w square by 2 alpha t. So where alpha is defined as the limit of s square by t, where s and t both tends to 0. So if we define, if it has two outcomes, plus 1 and minus 1, then again it is expected that the expectation would be 0, because as time goes to infinity, the number of points of plus 1 and minus 1 would always be same. That is the case. And also the autocorrelation of t1 comma t2 is defined as minimum of t1 comma t2 in multiplied by alpha. Yeah, so that's it for question number 1. Thank you.